Okay, so what? Okay, it's streaming now. So it's streaming into my YouTube channel. I'll just send you the link later. Okay, so what do you have today? What are you? Okay, wait, hold on. I think you when we were doing radioactivity, I left you one last question, but you didn't have to answer it, right? The question was, would you rather swallow some strontium 90 or have it put on your skin?
Uh, I didn't really take that note down to answer that question.
Okay.
Sorry. I
Okay.
don't know that paper. My bad.
But what do you think? Would you rather ingest it?
Could you repeat the question, please?
Okay, would you rather ingest strontium 90 or place it on your skin? Okay, I'll give you a hint again. Strontium 90 decays with yeah, it undergoes beta decay, right? So if we go back to penetrating power first, if we go back to penetrating power, gamma would be somewhere in between, between alpha and beta, alpha and gamma, right? So if here's the thing, alpha particles can be stopped by paper, right? So your skin should be enough to stop alpha particles, right? Beta particles, on the other hand, can pass through paper but can be stopped by an aluminum sheet. So in terms of your body, which one is gonna get deeper into your body, alpha or beta?
Beta.
Okay, so beta's gonna get in deeper, and then because of the fact that gamma radiation also has a higher ionizing power than alpha, so when the radiation goes into your body, it kind of gets stuck in the areas, in those actual areas where you don't want them to be, like your flesh or maybe your organs, like that, right? So in my case, I would just rather have it on my skin. There's an easier chance I
Wouldn't
can
that
just
be the
brush it
case for
off.
a lot of other?
Sorry, say that again.
Wouldn't that be the case? Wouldn't that be the case for a lot of evidence
Well, that's true.
you towards it?
That's true. But here's the thing. Since we have beta emission and we have beta radiation here, right? We have beta radiation. It doesn't really matter either way. It's gonna get into your body. Okay. If it's if it's alpha radiation that's being emitted, then I would rather just have it on my skin. It won't have that much penetrating power. It won't go through the skin too much. Okay.
Yeah.
All right. Okay. So the next thing we're gonna do, we're gonna go through the idea of half-life. Okay. Okay. Um, before we go there, before we go to this idea, I'm gonna ask you something that you should know the answer to anyway. So how many faces are there on on a die or on dice? How many faces does each one of those have?
6.
Six. So what are the chances of it one piece landing a six?
One out of 6.
One out of six. Okay. So dice have a 1 out of 6 chance to land on a particular number, right?
Yep.
Okay. Okay. The fact that this can happen, that there is a probability, means that dice, if you're given enough dice can have a half-life. Okay. This means that a collection of dice has a half-life. Okay. Okay. All right. I'm going to define what half-life is now. Okay. Half-life is the time needed for a sample of something to go from an amount x to an amount x over 2, or half of it. Okay.
Yep.
All right, that should be simple enough. So for example, I'll just give you an example. Let's say that you have this bunch of atoms here. I'm just gonna say atoms, right? And all of these are radioactive. Now, because the fact that they're radioactive means that after some time, it's going to decay. After some time, it's going to decay into something, right? Let's say that this is at element X. It's going to decay into an element Y, and it's going to decay into the particles, right? So I'm just going to say alpha or beta, right? But more importantly, you still have some amount of X. Not all that X will disintegrate or decay, right? Let's say
Yep.
that this is X over 2, okay? So this time here is called the half-life. This is the half-life, okay? All right. So that's a key idea. And the half-life really depends on the element, or depends on the element or the nuclide, okay? Or the isotope.
Yep.
I'll give you an example of this. For example, what's a good example here? Let's just say uranium, okay? So when you have uranium, there are several forms of it, as we already know. The two most common types are uranium-238 and uranium-235, right? Okay. The
Yep.
half-life of uranium-238, so if you have uranium, again you have 238 uranium and you have 235 uranium. This has a half-life of around 4.5 billion years. Okay, so very long. It's so long that you can consider it stable, right? Okay,
Yep.
uranium 235 on the other hand, let me just double check half-life. If I'm not mistaken, this is around 500 million years. I'm just gonna make sure of that value. But oh, yeah, I was more or less right, but not exactly. Uh, this has around 700 million years. So you can see that uranium-235, because of the fact that it has fewer neutrons, has a different half-life than uranium-238. Okay, how exactly? Well, at our level, we can't really predict it. There's a way to predict it, but it will still involve quantum mechanics. So for now, we will not look at how exactly to predict that. Yeah. Okay. Of course, there are some other elements. For example, what's a really good element? Technetium. Um, the half-life of technetium. Let me just check. Technetium has a half-life of technetium 99. Okay, technetium 99, TC 99. It has a half-life of around 6 hours. Okay, and some elements, yeah, some nuclides have like half-lives of micro or milliseconds. Okay, all right. So okay, that's enough talk about half-life. Um, so this is what we'll do. We're gonna do a dice game real quick here. Okay, so
Okay.
okay, Control T. Okay, let's remove this first. Okay, what I'm gonna do is I'm gonna visit a site. It's called random.org/dice. Okay, I'm gonna post that link on the chat box. Okay, so you can visit this site as well. Okay. Now, if you're gonna
Okay.
visit that, if you wanna just go along with this, you can do so. But if you wanna visit the site, you can do so as well. Okay. Now, when we do this, let's just allow selected here first. Okay. When you go there, let me share my screen there with you so you can see it. Random.org. Okay, so here you can see that we can change the number of dice we can roll. The maximum number we can roll is 60 dice. Okay, so the idea here now, if we go to the Jamboard, I'm gonna give you a very simple set of instructions. Okay, roll. The first one you're gonna do is roll the maximum number of dice. So in this case, 60, right? Okay. The second instruction here is select one number. So 1, 2, 3, 4, or 5, or 6. Select a number on the dice. So from 1 to 6. Okay, so for example, I'm going to select 6. Okay, now once you roll, once the roll is done, all you have to do now is count the number of dice that come up as, what's this? Come up as the number you selected.
Yeah, sorry, just 1 second. Sorry.
Okay, go ahead.
I'm sorry, so just 1 second. Someone's making order.
Okay. So for example, let's say that on the random.org, that on this random.org thing, we have 60 dice to start with, right? Okay, so if I roll the dice,
Yep, sorry.
okay, so in this case, I've rolled the dice, and this time, let's say I'm gonna select the number 5. Okay, so let's count the number of let's count the fives here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 dice, right? So, okay. So what I'm going to do now is I'm going to record the information on this table. Okay. So I'm going to start off with 0 here, and I'm going to start off with 60 here. Okay. Then on the first roll, this is the number of rolls. How many dice turned up 5? I got 12. So I'm going to do 60 minus 12. And I'm going to end up with 48.
48.
Okay. So what you're going to do now is on your roll 2, you're going to start with 48 dice. Okay. So once I go back, if I go back here, I'm going to change this number.
So how does that relate to physics though?
Okay. This is, I'm going to tell you something first, okay? How does this relate to physics? Okay, I want to ask you something. Can you like predict which die or which dice are going to come up 5?
I can't predict.
You cannot predict. You can only but you do know that there's a chance, a 1 in 6 chance that any one die will come up as a 5, right? So that's the one part of radioactive decay. It's random. It's like dice. You don't know which atom, which molecule is, or which nucleus is going to decay. You just know that there's a chance that this molecule or nucleus will decay. All right? So that's the first part. Okay, the second part is half-life. You will see that because, again, of this probabilistic nature, we will get a number for the half-life just because we know that 1 out of 6 of these dice will disappear. Okay, and this is what we'll do now. So if we go back, we'll change the number of dice to 48, right? And we're gonna roll that. Okay, so let's count 5 again, right? So if you count 5s, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I got 15. That's kind of strange, but still within reason, right? So I'm gonna do minus 15. So that's gonna leave me 33, right? And I'm gonna the task here, and I want you to do this on your own. This is gonna be me. Okay. Now, Adam, I want you to put your results here. So you're still going to put 60 here. Okay. Your goal is to get to 0. Okay.
Okay.
All right. Let's do that. And then what I want you to compare as you do that is whether we get the same answers or not. Okay. All right. I think you should be able to do this
But
in
it can
about
be a
3
random
minutes.
number.
I'm also gonna do this. Yeah, I'm also gonna do this. So we're gonna continue. So I'm gonna put 3.
I was gonna ask that. So I also opened random.org.
Yep. Please open random.org again. Okay. All right. There we go. If you're able to edit the Jamboard, right? Okay.
Jim. Yeah.
Okay,
I
go
kind of
ahead.
already have it open.
Okay, go ahead then. 33.
So I started 60, right?
Yeah, you start with 60. Okay, I'm just gonna continue my dice rolling here. Okay. 1, 2,
Wait,
3.
what number do I start with? Is any
60.
number?
You start with 60.
No, I mean like which number do I count?
That's up to you. You can select.
Okay.
So, for example, you select 5 as well. Do 5. If you want to select 1, select 1. Okay. 2, 3. You got 3. So 33 minus 3, 30. Okay. Okay, Adam, while you're doing this, I just want to make sure, yeah, you are familiar with using either Google Sheets or Excel, Microsoft Excel.
Uh, kind of.
Kind of is good enough. Kind of is
I
good enough.
don't use. Yeah.
Okay, that's fine. I'll just show you later what we're gonna do with these numbers. Okay, 25. Okay, just a heads up, yeah. When I do this with my class, some students go really fast, like within 10 rolls, they're done. The longest
Oh,
the longest amount of time that a student has done this with me, uh, 35, I think, 35 rolls before they got to 0.
that's a lot of rules.
Yeah,
That's as if you go one. That's as if you go like two per rule.
yeah. Okay. Oh my gosh, I think I'm gonna be one of those long ones right now. 25 minus 3, 22. Okay. I think I'm gonna open my own what's this? My own Google Sheet right now, yeah? So hold on. Just go back to that first. Oh, hold on. How many roles are you in now?
6 rules.
6 roles, okay? Is this it?
What happens if I'm on 2 dice?
Sorry, say that again.
What happens if I'm on 2 dice?
If you're on 2 dice, you keep rolling until you get to 0. If both of them roll up to 1, to whatever number you have, then that's the thing, yeah? Yeah.
Good. I'm on 0.
Oh, you're on 0. Alright, good. So, wait, hold on. Axis.
I got 9 spins.
Oh, you got 9. Okay. Alright. Now, what I want you to do now is I want you to graph. I want you to graph the number of rolls against the number of dice that you have left. So, for example, at 0, basically, I'm gonna show you something real quick. Yeah.
Okay.
Okay. Stop sharing first. I'll share this tab.
The higher
Okay.
the more spins, the
Yeah. Well, if you think about it, the number of atoms, or the number of dice in this case, that decay or that turn up to the number you say or you chose, it depends on the number of dice that you have, right? But the thing is, the probability of that number coming up is always 1 in 6. The actual number you'll get is probably going to be slightly higher or slightly smaller than that, but the average is around 1 out of 6, right? Let's just do it though. Okay, now I'm gonna show you some data right here. Okay, so this data is from all the classes I have had since last year. Okay, so whenever a class does this experiment, I always gather all of their data, add them up. So instead of having 60 dice, I now in this case have 660 dice, right? Okay, now I'm just gonna show you how to turn this into a graph. So in case you don't know how to, turn this into a graph, I'm going to show you how it's done. Okay, hold on first. Is this it? Yep. Okay, so in this particular case, if you look here, all you have to do is insert, then chart. Okay, now in this insert chart, this happens, and then we're gonna change this from a line chart to a scatter plot first. This way we don't get a connect the dots kind of graph, we get the dots graph. Okay, now I think you can see it clearly here that in my example, it's pretty smooth, right? Now what I'm going to do is I'm going to put a trend line on this. Okay, and of course I'm gonna make that trend line match as close as possible here. Okay, I think we got that at exponential. Okay, so in this case, what's happening is you can see that this graph kind of matches this the plots very well. So I'm going to put a custom label here. I'm going to put the equation in. The equation, it's just there so I know what I'm looking at, but you don't really need it at this point. Okay, It's here to me for me to confirm that this is in fact exponential. Okay, and you see it's e raised to some number x, right? Okay,
Yep.
but the key idea here is this. I'm just gonna well, not copy. Now here's the thing. We started off at 660 dice, right?
Yep.
What's half of 660?
Yeah, 660.
What's half of 660?
330.
330 would be somewhere around here,
330.
right? Somewhere around here.
Yep.
And if you look here carefully, what time did it go to? 330 is around what time?
4.
Around, okay, let's say between 3 and 4, right? We're not sure what exactly it is, but it's between 3 and 4. So if we do that same thing, if we go, let's use the average value first, 3.5, right? If you look at the next at the next time we're in, 3.5, you add 3.5 to that time, so you're gonna get to 7, right? When you get to 7, 7 is here. 330, half of 330 is 155. Is it?
115.
115.
115.
150. Okay.
115.
Okay. 150 plus 15, right? So that should be 165. Or let's say 160-ish.
Are you asking for 165?
Because half of 330, right? 330 is here.
Half
So-
of 330 is 115.
No, it's 165. Right?
1/3.
300, half of
Sorry.
300 is 150. Half of 30 is 15.
Oh my god, I'm so dumb.
That's okay. It's okay.
Um,
Right. So 165, right? If we go to times 7,
Yeah.
look, if we look at this time wherein it's 7, our value is again close to 165, right? So what's half of 165 again?
I'm not gonna guess anymore.
Okay, calculate. It's fine. Use your calculator. What's half of
Isn't it
165?
like 82.5, right?
So let's go to 82, right? I'm gonna say that 82 is around 10. Is around that time 10.5, which is gonna be here. Look, that's 86. That's 70, right there. You see the magic that's happening? The fact that we have something that decays due to a probability, it's gonna have a half-life. In this case, the half-life of rolling dice is every 3.5 rolls, you get to half the original amount or the previous amount. So our half-life for dice is 3.5 rolls. Okay?
Okay.
Make sense?
Yeah.
Okay. So of course, in terms of what we do, this is what we do when we have dice, right? But in terms of what we do for half-life with nuclei, the same idea applies. Okay. So, so I'm just gonna go back here first. Let's stop sharing for now. Okay. Okay, I'm gonna take a look. I'm gonna look for a problem somewhere first. I'm okay. Hold on. Okay, practice problems. Okay, so I'm going to give you a very simple question first. I'm taking this from the internet. I'll just put the citations later for the sake of the video. Yeah, but if we go to the board, and where is the jam board? Okay. So here's a problem first. It's gonna take a while. Okay, so we have an isotope. Cesium 137 has this half-life, 30 years. So if you start off with 1 gram, if 1 gram disintegrates over a period of 90 years, how many grams would remain? Okay, so you have a total of 1 gram to start with. Okay, so the idea here is the best way for you to do this is to take a look at the half-life first. Okay, so the half-life is 30 years. So what you count here is you count here. How many half-lives is this? 90 years compared to 30 years. So 90 years would be equal to 30 years times 3, right? This
Yep.
thing is the number of half-lives that you have gone through. Okay?
Does it have to be like, oh, like, how do you exactly find that midpoint?
You will always be given one of the following. You're always given the half-life, the amount of time that you have, or the number of half-lives. Two of those will always be given. Okay? So how what would we do here? The next step is we're going to take this number of half-lives and we're going to divide our sample by 2 raised to this. Okay, so what we're going to do is we're going to take 1 gram and divide that by 2 raised to that number here, right there. Okay, so that's going to become 1 gram divided by 8, and that's going to leave you what's 1 over 8? 0.125 grams, right?
Yep.
Right? So this is our answer here. Okay? Remaining. Alright? So this is how you would solve problems with half-life. That's the first one. If you're, again, given the number of years or the amount of time that you have, you're given a half-life and you're given a certain amount. It could be mass, it could be number of particles, could be some other number. All you have to do is keep dividing that number. This 1 gram here, just to make sure, comes from here. Okay, goes there. Okay, clear?
Okay.
All right. Hold on. Where did it go? Okay, I'm just going to... Okay, there we go. Okay, so... Alright, so another problem we're going to be looking at is... Let's just do the same source. Okay, here is another thing. It's going to be very similar to what we've done. Okay, but this time, for number 2, question number 2, we have the selenium 83 has a half-life of 25